Hello everyone, hope you are doing well. Welcome back. Today we're going to look at two statistical tests that can be used to test whether one or possibly more samples are coming from either a normal distribution or just some distribution in general. And those tests are referred to as the Kolmogorov-Smirnov and the Lilliefors test. So what is the hypothesis test that we're going to be looking at today? So the general null hypothesis is that the distribution associated to our population is equal to some claimed distribution of that population. And the alternative that we're going to be looking at is that the distribution of the population is not equal to the claimed value of the distribution of the population. So we're going to be primarily focused on a normal distribution for our claimed distribution for these samples or populations. But technically you can use the Kolmogorov-Smirnov test for any population for which you're interested in sampling, such as a log normal or an exponential or something like that. So just a couple notes here just in case you're curious. Phi can either be continuous or it can be a discrete distribution, for example, like a Poisson or a binomial or something like that. So since we're estimating a population distribution and that population distribution is called phi, what do we need? Usually when we're doing hypothesis testing, we need a point estimate. Right? So what is a point estimate for a distribution? We're going to be calling the point estimate f, where f is going to be referred to as the empirical distribution, which typically is going to be a discrete distribution, regardless if we're trying to approximate a continuous or discrete distribution. Okay. Now keep in mind, if we're going to be testing the normality of a distribution, you should be able to at least get a sense whether our sample is coming from a normal distribution via, say, a normal quanta-quanta plot. That's a qualitative method, but we're looking, for example, for a quantitative statistical method in order to test whether our sample is, in fact, coming from a normal distribution. So how are we going to start this analysis? So let us suppose that, let's call this distribution actually psi of x. So let's call psi of x is the cumulative distribution function, of the probability density function phi, right? So if our distribution phi and phi 0 are equal to each other, that means the cumulative density functions of those functions are also equal to as well. So that means what? So that means psi of x is going to be equal to the cumulative density function of the claimed distribution, and the alternative would be, of course, psi of x is not equal to psi 0 of x. Now let's just briefly talk about, what exactly is a cumulative density function. But first off, what is a point estimate? So if little f is going to be the empirical point estimate for phi, we're going to be calling the point estimate for psi, we're going to be calling this capital F. So capital F is going to be the cumulative empirical distribution function of the random variable we're trying to estimate. So let's briefly review what exactly is a cumulative distribution function, and we're going to briefly be talking about, why we actually prefer to do hypothesis tests on the cumulative distribution function, not actually the original distribution. So since our primary focus is going to be normal distribution, we should know what a normal distribution looks like, right? So this is going to be equal to phi, and as we already know, most of the area, at least 99.7% of it, is usually between -3 and 3. So what is the cumulative density function associated to a normal distribution? So remember, all of the area underneath the probability density function is equal to 1. Therefore, the maximum value for which a cumulative density function can take is always going to be equal to 1, whether we're working with a continuous or discrete probability density function. So notice that 50% of the data is to the left of this value. So that means this is going to cross at x equals 0 at the value of 0.5. Notice when we're at x is equal to -infinity, we have no area underneath the curve, and then it's going to slowly increase, and then it's going to get to 0.5, and then it's going to slowly increase and go to 1 as we get over and closer to positive infinity. So this distribution shown in purple, this is psi, and this graph in blue, this is phi. Okay, so we're going to be approximating phi with f, and we're going to be approximating psi with capital F, where capital F is the cumulative density function associated to little f. And in case you don't know how to calculate, for example, discrete cumulative density functions from discrete PMFs, you can definitely refer back to, say, frequency distributions or something like that. Now, before we get into the Kolmogorov-Smirnov test and how to execute it, I just want to make one thing very, very clear in case you are not already aware of it. So, if phi1 of x is equal to phi2 of x, this can be proven to show that the cumulative density function of 1 is actually equal to the cumulative density function for 2. But if the cumulative density function of 1 is equal to the cumulative density function of 2, this does not necessarily imply that the density function of 1 is equal to the density function of 2. Okay, so let's just do a quick example just to give it a counterexample of this second claim that somebody might make. So let's assume that we have a normal distribution here. And let's assume that we have another distribution that has a removable discontinuity, say x is equal to 0, and let's put its value, say, there. So one can show from the continuous perspective that the areas under these curves are equal to each other at every single point in the domain, but both of these have the same exact CDF that is going to look something like the one that I shown before, right? So if that's a 0, and that's 0, and that's 0, they both have the same exact CDF, right? So just because they have the same exact CDF does not necessarily imply that the distribution of them are equal to each other. They could be unequal to each other at, for example, a countable number of removable discontinuities, or something along those stages, okay? So those are just some basics associated with cumulative density function and a couple little theoretical properties. Now let us get into the Kolmogorov-Smirnov test and how we can use it to test the normality of a particular sample that we've drawn from a population. So let's assume that we're interested in sampling some blood pressures from a population, and let's assume that we actually require that sample to be from a normal population. For example, we might be doing an F test, a T test, a Z test, or something along those lines, which all of them require, for example, normality. And if the population doesn't appear to be normal, then those tests might be misleading or provide us with inaccurate results. So let's assume that we are trying to test if we have evidence to believe that the population we're sampling from is actually normally distributed with a given mu of 121 millimeters of mercury and a variance of 2.1 squared millimeters of mercury. So the difference between the Kolmogorov-Smirnov test and eventually the Lilliefors test is Lilliefors does not require us to actually know the mean, or it doesn't claim any values about the mean and the variance. It just says, oh, do we have evidence to believe that it comes from a normal distribution? I don't really care which one. The Kolmogorov-Smirnov focuses on a particular normal distribution. So that's the primary difference between these two things, right? So let's start off with the Kolmogorov-Smirnov, and then we'll switch into Lilliefors for our second example. Okay, so let's just quickly state a sample that we may sample from some population that we're interested in testing the normality of. Let's assume that these are the sample values that we collected from some population. So notice that we have 1, 2, 3, 4, 5, 6, and 7. So we have a sample size of 7. And we want to, analyze, from this sample, do we have evidence to believe that the population we're sampling from is normally distributed? Now, as usual, if our sample size is sufficiently small, we might get misleading results, right? And since I'm just using a sample size of 7, I might be getting misleading results from this test as well, right? But I'm just keeping the sample size small so you can sort of work with the logic that the Kolmogorov-Smirnov test is actually going to execute, okay? So what is the distribution that we're actually trying to propose here, right? So we're trying to see if we have evidence to believe that the sample is coming from a normally distributed population. Let's call it phi. Okay, so if it was exactly normally distributed, at least a discretely normally distributed sample, x4 is going to be located in the middle, right? And how do I get 4 so quickly? That's going to be m plus 1 divided by 2. So that's the median of an odd sized data set. And then x3 is going to be located somewhere there. x5 is going to be its mirror image over there. x2 is going to be located a little bit farther than 3 compared to 3 from 4. And then x6 is going to be located there. And then x1 is going to be located over here in the tail. And then x7 is going to be its mirror image as well. So what are the areas in each of these locations? So let's draw some vertical lines here. So if these are truly normally distributed, what is the area in each of these pieces? So the area in this little piece should be equal to, so how many pieces am I chopping up my distribution? So 7 points is going to partition that area into 8 regions. So that's going to be 1 over 8. This area here should be 1 over 8. That should be 1 over 8. That should be 1 over 8. And by symmetry, that should be 1 over 8, 1 over 8, 1 over 8, and finally 1 over 8, all totaling to 1 because it's a probability density function. So how do you get this particular number there? So each of these probabilities is going to be equal to 1 divided by the number of values in your sample plus 1. So we have 7 samples, so that's going to be 1 divided by 7 plus 1, or 1 over 8. All right, so that's a N7 or a discrete sample size normal sample of that sort of, we can use as our empirical distribution comparison. So let's look at the cumulative density function perspective of this. All right, so it's going to be looking similar to that. Okay, so let's draw our percentages, for example, 1/8, 2/8, 3/8, 4/8, 5/8, because up to x1 the value should be 1/8, up to x2 it should be 2/8, up to x3 it should be 3/8, and then up to x4 it should be a half, right, or 4/8. So let's draw our values there. That's not really symmetric. Let's draw a line a little bit there so it looks a little bit more symmetric. So 4/8 should be there. And then 5/8 should be there, and then 6/8, and then 7/8, and then we're going to have 3/8, 2/8, and 1/8. So if we draw where these points are coming from, so that should be x4, x5, x6, x7, and then over here we have x3, x2, and x1. Right, so that is our distribution psi, and that's our distribution phi. Right, so that's the graphical perspective of what we're looking at here. So, how are we going to conduct a Kolmogorov-Smirnov test with respect to our sample data? So we know what the CDF and the PDF of these empirical distributions should look like. Now we can compare those values, the theoretical ones, to the values that we actually have. Okay. So let's just ask a question that we need to answer. So what points, moreover quantiles, do the sample values correspond to in our proposed cumulative density function psi? Right. So remember, our distribution that we're sampling from is a normal distribution with a mean of 121 and a variance of, 2.1. Right. So let's just make a little table to organize all our values. So our sample values were, let's just list them out here, 121.3, 121.7, 122.3, 122.4, 122.9, 131.4, and lastly 133.7. Okay, so what values are they associated to our normal or to our true cumulative density function? Okay, so how do we find these values? So these values are the probability that little x or capital X is less than these little x values, right? So what is the probability that a person has a blood pressure less than 121.3 if we're sampling from that distribution? So you should know how to do those probability values. So that's going to be approximately 58%. Now, why is that so high? Because notice 121.3 is higher than our mean 121, so that means the probability should be at least 50%. Right? And this is a monotonic increasing set, so all these probabilities will be bigger than 50%. And you can find that that's going to be equal to approximately 69%, 82%, 83%, 91%, approximately 1, and approximately 1, but not equal to each other. I'm just rounding to 2 decimal places here. Right. Now, those are the theoretical values that these points in S are associated to, and what values do we want to compare them to? So that's going to be our empirical cumulative density function, right? And we already know that the area to the left of 121.3 should be equal to 0.125. That's 1/8. And then 2/8, and then 3/8, and then 4/8, which is a half, and then 5/8, then 6/8, then 7/8, and then 8/8 would be infinity, which we're not comparing to. All right. So, is there a significant difference between these quantile values in the CDF? That's what the Kolmogorov-Smirnov test. So, just a couple analytical things to keep in mind. So, the maximum possible value of the absolute value of psi x minus f of x. You may want to pause the video and think about this for a moment, but what is the maximum possible distance between psi and f? You should be able to show that that is going to be equal to 1. For example, all of those values should be between 0 and 1, so one could be 0, the other one could be 1, and that's the maximum distance they could be. So what we're going to do is define a distance metric, let's call it dk, and this is going to be equal to the absolute value of psi kx minus fkx. And here k is going to range from 1, 2, all the way down to m. So we're just going to be comparing these theoretical values to these empirical values and look at the absolute distance between each of them. All right? So what is that going to give us? So for our sample values, let's just list out our little table. Let's just pause the video for a moment and calculate that if you want to. So if you calculate all of the values for those sample and theoretical values, you should get those distances between our psi function and our empirical f function. All right. Now remember, if these two distributions line up perfectly, then the cumulative density values should be equal to each other, and hence the distance between them should be equal to 0. So what we want to see is, well, if they're very different, then for example, the maximum distance should be significantly large. All right. So what we're going to do is we're going to define our test statistic, which is the Kolmogorov test statistic, which is going to be the maximum of our distance values. All right. So if you choose the maximum of all of these values, notice that our maximum is generated by point number 1. Therefore, our Kolmogorov test statistic is going to be equal to approximately 0.475. Right? And remember, the maximum value that the k-stat can be is equal to 1. So is our k-stat significantly large? So is k-stat large enough to reject the null hypothesis that our distribution is actually coming from a normal distribution? So how can we, make a little decision tree? So if our Kolmogorov-Smirnov test statistic is larger than some critical value, so we need to figure out, well, how are we going to calculate a critical value? So if that is true, once we're able to find such things, we're going to be rejecting the null hypothesis. All right. So this is going to be a one-tailed test. Okay, so how are we going to generate our critical values for Kolmogorov-Smirnov test? So this is where, for example, Monte Carlo simulations do have their highlight, because generally speaking, for complex distributions, you might not have tables, or you might not know the true distribution that this test statistic actually follows. Okay, so how would you set up a Monte Carlo simulation to generate, for example, an empirical critical value or an empirical p-value associated to this test? So what we're going to be doing is we're going to generate a series of samples from a normally distributed population whose mean is 121 and its variance is 2.1 with a sample size of 7. All right, and how many samples do we want to iterate? Well, a good iteration is probably 1,000,000 different samples from that population with sample size of size 7. Okay, so how does this Monte Carlo simulation go? So what we're going to do is we're going to calculate the Kolmogorov test statistic for all of those samples. So you may want to do this, for example, in R or MATLAB or some other platform. And then the question that we need to ask ourselves is, what percentage of these k-stat values are greater than our k-stat value? So do you know what this question is equal to? That's actually the definition of a p-value, right? The probability of getting our test statistics or something more in favor of our null hypothesis, right? And we want it to be as large as possible in order to reject. So you should be able to find, at least via some Monte Carlo simulations, as long as your number of iterations is significantly large, that the empirical p-value for this is approximately equal to 0.8947. Up somewhere in that realm, probably anywhere between 85% and 90%, you should get values associated to that. Right, so this p-value is significantly large. Even if our number of iterations is significantly smaller than 1 million, our p-value is definitely still a little bit larger than it should be, right? So since our p-value is large, that means we're going to be failing to reject the null hypothesis that our population that we're sampling from is approximately normal. That means we have evidence to believe that our sample set is approximately normally distributed, which is actually a very good thing. Now, you may not want to be working with p-values. You may want to be working with, for example, test statistics. From all of our k-stats for 1 million iterations, you of course will have an empirical distribution that this test statistic actually follows, and you should be able to find that if alpha is equal to 0.05 or 5%, which a lot of people like to deal with, our k critical value, or an approximation of it, is approximately 0.8498. So that is the minimum value of a test statistic for the Kolmogorov-Smirnov test that we would have to have in order to reject the null hypothesis under an alpha value of 5%. And again, you can obtain that value from a Monte Carlo simulation if you actually don't know the value or the distribution of that thing, or you might not have any tables associated with that particular test, right? And that is the Kolmogorov-Smirnov test for testing the distribution of a particular sample, or the likelihood that that sample comes from that distribution you specify it to be. Now that we know how to test null hypotheses associated to, a resampling from a particular normal distribution, now let us take a look at the Lilliefors test, which can be viewed as a special circumstance or a special subset of the Kolmogorov-Smirnov test. So what the Lilliefors test actually tests is, does our sample appear to come from a normal distribution? Because remember, for example, regression, ANOVAs, and things of that sort, we don't really care which normal distribution is coming from. As long as it's normally distributed, that's usually okay. All right. So for the Lilliefors test, we do not require a mean or a standard deviation or variance parameter to be known in order to conduct a Lilliefors test, which is typically a realistic thing because we usually don't know what those parameters actually are. So this normal that I'm specifying here is any normal distribution. So what we're going to be doing is we're going to be approximating mu with its point estimate x bar, and we're going to be approximating sigma squared with its point estimate s squared. Right? And actually a safer way, instead of comparing, for example, whether our distribution is coming from a normal distribution with a mean of x bar and a variance of s squared, what we can actually do is actually look at the z-scores of our values and then compare that to, for example, a standard normal distribution. That's usually a safer way to go when you're actually going with a Lilliefors test. Okay, so keep in mind the probabilities associated to a normal and a standard normal distribution are the same exact thing. The only thing that changes is the domain of those values. So we're going to be comparing to empirical values associated to a standard normal, but the empirical values of our standard normal is going to be the same ones as we had before. So the very first value is going to be 0.125, 0.250, 0.375, and 0.500, 0.625, 0.750, and 0.875. So those are the same exact empirical values, but we're focusing on the z values instead. Right? So we need to calculate the theoretical values that these Sx values are actually associated to a standard normal distribution. Therefore, the very first thing we need to calculate actually should be the z-scores associated with that, right? So remember that the z-score for a particular x value is going to be x minus the mean divided by the standard deviation associated to that particular value, right? Now, it's highly recommended that you might want to remove outliers just in case you suspect any, but we're not going to do that here. So the z-scores are going to be negative 0.74, negative 0.65, negative 0.54, negative 0.52, negative 0.43, 1.22, 1.67. Notice that we have 5 negative values and 2 positive values, so we definitely have some evidence of skewness, right? Which is definitely a bad thing because we should have an equal amount of positives and negatives in our data set, or something close to that. There shouldn't be a substantial difference between those percentages. And you should be able to find the associated cumulative values associated to these values. So how do we calculate? So the probability that capital Z is less than these values, which we should know how to do with respect to a standard normal distribution, is going to be equal to 0.23, 0.25, 0.29, 0.30, 0.33. Keep in mind, all of the negative z-score values should have CDF values less than 50% because we're to the left of the mean, which is 0. And then 1.22 now that we're to the right, so we have a value that's bigger than 50%, in particular 89% and 95%, right? Because remember, 1.67, that's approximately like that, 5% critical value that we should already be familiar with. Now, what are our questions for the Lilliefors test? And this is going to be similar to the Kolmogorov-Smirnov case. So is there a significant difference between these percentile values here? Is there a significant difference between them? Because if they are truly coming from the exact same distribution, then those CDF values should be equal to each other. Okay, so what are we going to be calculating? So the Lilliefors test statistic, which I'm going to abbreviate as LI-stat, this is going to be approximately equal to 0.290. And again, this is going to be equal to the maximum of the distances between, so the maximum of the absolute value of f of z minus phi of z, or phi of z minus f of z, is the same exact thing, across all z values in our data set. Okay, so we have that particular value. Now notice that it's lower than our k-stat value, right? Because notice that since we're sort of focused on the x-bar of our sample, it's a little bit more centered to a normal distribution, so we're sort of given it a little bit of leeway here in terms of that. So we shouldn't be surprised about that. Okay, so now we need a critical value or a p-value too. So what we're going to do is we're going to do a Monte Carlo simulation in order to generate those critical values and p-values. So one should be able to show that the empirical p-value associated with this is approximately equal to 0.9904, right? Which is higher than normal because, well, we shouldn't be surprised because we're sort of centering a normal distribution around it. So as usual, we're going to be failing to reject the null hypothesis. And you should also be able to show that a 0.05 level of statistical significance is going to generate a critical value of approximately 0.8497. And if you refer back to the Kolmogorov-Smirnov critical value for an alpha value of 0.05, notice that they are at least empirically equal to one another, right? But they're actually not going to be equal to each other. The difference between a Lilliefors critical value and a Kolmogorov critical value is actually going to deviate more when you get to the tails. So when you get larger than 95%, when you get less than, I don't know, something along like 25% or so, that's where the critical values actually start to deviate a lot. They're going to be deviating a lot at the tails. But when we're in the middle range, the Kolmogorov-Smirnov and the Lilliefors critical values are usually, approximately equal to each other. But nonetheless, we're going to be failing to reject the null hypothesis that this sample is actually coming from a normal distribution, which means we have evidence to believe that it's at least close to normal. So we can do, for example, our chi-square test, f-test, t-test, and so on. Okay, so let's just summarize a couple tests before we part ways for today. Right. So the very first test that we talked about today was the Kolmogorov-Smirnov test. And this tests whether a particular population is normally distributed with some particular mean and some particular variance. But if you're not very picky on that mean and variance, then you can of course shift to the Lilliefors test to test for normality regardless of the distribution. Now there are other tests out there that are a little bit better than the Kolmogorov-Smirnov and Lilliefors in the general sense. And let me just mention them here. We'll talk about them possibly another day. But the first that you may want to sort of investigate is known as the Anderson-Darling test. The Next one would be the Kramer-von Mises test. And then the last test will be the shapiro-wilk test. Okay, so those are some other statistical tests that are usually a lot better, generally speaking, than the Kolmogorov-Smirnov and Lilliefors test. And typically the Anderson, Darling, and Kramer-von Mises test are about equally good, and at least at the present time, the Shapiro-Wilks tends to be the best across all 5 methods for the general scenario of testing the normality of a particular population or testing the potential normality of a particular sample. So that's some hypothesis test associated to testing the normality or moreover the distribution of a sample. I hope you enjoyed, and I'll see you in the next video. Take care.